Welcome to Ultimate Sleep Doctor. Tonight, we'll be exploring a world unseen, a realm of incredible detail. Let's drift into the fascinating world of nanotechnology, where matter itself is measured in billionths of a meter. These are the building blocks of the future, tiny machines woven into fabrics, delivering medicine and reshaping our world. Consider the immense power contained within something so small, like a single drop of water, endlessly divisible. It's a beautiful paradox, isn't it? A vast potential held within the infinitesimally small. If you find the pursuit of knowledge a comforting embrace, perhaps this exploration will ease your mind. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe, let your thoughts drift, let's begin. The story of nanotechnology began not with a gleaming lab filled with tiny robots, but with a single, brilliant idea. In 1959, Richard Feynman, a Nobel Prize-winning physicist, delivered a talk titled, "There's Plenty of Room at the Bottom." He wasn't describing a new technology, but a fundamental shift in how we thought about manipulating matter. Feynman argued that we should be able to work at dimensions far smaller than we currently do, at the scale of atoms and molecules. He envisioned a future where we could build machines atom by atom, manipulate individual molecules, and even repair damaged cells with incredible precision. If we could only manage to handle individual atoms and molecules with some degree of precision, he said, we might be able to make a fabric that's 1 billion times stronger than steel, or a machine that's 1 million times smaller than a computer. He didn't have the tools to do it then, but he planted the seed, the audacious notion of controlling matter at the nanoscale. Interestingly, the term nanotechnology itself emerged a little later. In 1974, Norio Taniguchi, a professor at the Tokyo Institute of Technology, used the term to describe precision manufacturing at the micro and nanoscale. Taniguchi's focus was on improving existing manufacturing processes, things like polishing semiconductor wafers, using smaller and more precise tools. This initial definition was more about production techniques than the revolutionary potential Feynman had envisioned. However, Taniguchi's work helped to legitimize the field and provided an early framework for exploring the possibilities. The truly transformative ideas, however, began to take shape in the 1980s with K. Eric Drexler. Drexler, a brilliant young scientist, took Feynman's vision to its logical extreme, proposing the concept of molecular machines. He imagined incredibly small, self-replicating machines, perhaps only a few nanometers in size, that could be programmed to perform a vast range of tasks, from building complex structures to diagnosing and treating diseases. These machines, built from individual atoms and molecules, would be controlled by information, much like a computer program. Drexler's work, outlined in his book Engines of Creation, sparked intense debate and inspired a generation of scientists. Early experimental research focused on manipulating materials at the atomic level. Scientists, often funded by the U.S. Department of Defense and later by government agencies like the National Science Foundation, began to develop techniques like scanning tunneling microscopy, SDM, and atomic force microscopy, AFM. These tools allowed them to see, and to a limited extent, touch individual atoms and molecules. Achieving true nanoscale control, however, proved incredibly difficult. The forces involved at such small scales were incredibly weak, making it challenging to precisely position and manipulate atoms. As research progressed, concerns began to arise, largely fueled by Drexler's ideas. The gray goo scenario, the theoretical possibility of self-replicating nanobots consuming all matter on Earth, became a popular, albeit often sensationalized, topic of discussion. The potential for such uncontrolled replication prompted serious consideration of safety protocols and ethical guidelines. While the gray goo scenario remains largely theoretical, it highlighted the need for careful research and responsible development within the field. Research institutions like MIT and Caltech became key centers, fostering collaborations and pushing the boundaries of what was thought possible. The early years were characterized by both immense excitement and cautious skepticism, a healthy balance that continues to shape the field of nanotechnology today. Let's delve now into the heart of nanotechnology, the creation and study of some of its most remarkable building blocks: carbon nanotubes, graphene, and quantum dots. These materials, defined by their incredibly small size, exhibit properties that are dramatically different from their bulk counterparts, opening doors to a huge range of technological possibilities. The journey to making these materials begins with synthesis. Carbon nanotubes, those incredibly strong, hollow cylinders of carbon, can be produced through several methods. Chemical vapor deposition, or CVD, is a common technique where a gas containing carbon precursors is heated in a reaction chamber, allowing carbon atoms to assemble into tubes. Arc discharge, mimicking a miniature lightning bolt, also generates nanotubes by creating a plasma that breaks down carbon materials. Laser ablation, using a pulsed laser to vaporize a carbon target, is another effective route. Each method presents its own set of challenges. Controlling the diameter of the nanotube is tricky, as is manipulating their chirality, the way the tube twists, which affects their electrical properties. Furthermore, defects within the structure can significantly impact their performance, and researchers constantly strive to minimize these imperfections. Graphene, a single layer of carbon atoms arranged in a honeycomb lattice, presents a different synthetic pathway. Mechanical exfoliation, famously pioneered by Andrei Gime and Konstantin Novoselov, involves repeatedly peeling off layers of graphite using adhesive tape, a surprisingly effective method for producing high-quality graphene. Chemical vapor exfoliation employs plasma to break down graphite into individual graphene sheets. Controlling the size and purity of graphene flakes remains a significant hurdle, but advancements are continually improving the process. Finally, let's consider quantum dots. These tiny semiconductor crystals, typically made from elements like cadmium or indium, are engineered to emit light of specific colors when excited. Their size dictates the wavelength of light they produce. Smaller dots emit blue light, larger dots emit red light. Quantum dots are synthesized through various chemical reactions, carefully controlling parameters like temperature and precursor concentration. Once these nanomaterials are created, characterization becomes crucial. Raman spectroscopy is a powerful tool for identifying the vibrational modes within the material, providing insights into its structure and quality. Transmission electron microscopy, TEM, offers direct visual confirmation of the material's nanoscale structure, revealing the arrangement of atoms and the presence of defects. Atomic force microscopy, AFM, allows scientists to probe the surface topography of these materials at the nanoscale, measuring their mechanical properties like stiffness and adhesion. X-ray diffraction, XRD, is used to determine the crystal structure and lattice parameters of the materials, providing further information about their atomic arrangement. It's important to recognize that nanomaterials aren't perfectly uniform. There's always statistical variation in their properties. Some nanotubes will be thicker than others, some graphene flakes will be larger than others, and quantum dots will have slightly different sizes. Understanding and accounting for this variation is key to predicting and controlling their behavior. The unique combination of these properties, exceptional strength in carbon nanotubes, outstanding conductivity in graphene, and tunable optical characteristics in quantum dots, makes these nanomaterials exceptionally valuable for a wide range of applications, from electronics and energy storage to biomedical imaging and sensing. The human body, a remarkable and incredibly complex machine, often struggles to deliver medicine precisely where it's needed. Traditional treatments sometimes flood the entire system, leading to unwanted side effects alongside the desired therapeutic effect. Nanotechnology offers a revolutionary solution, shifting the focus from broad-spectrum treatment to targeted delivery at the smallest scale. We're talking about materials just billionths of a meter in size, so tiny you can't even see them with a regular microscope. And they're being engineered to tackle some of medicine's biggest challenges. One of the earliest and most successful approaches utilizes nanoscale carriers like liposomes. These are essentially tiny bubbles made of fat-like molecules, capable of trapping drugs within their watery core. They circulate in the bloodstream, passively seeking out areas with leaky blood vessels, often found around tumors. Another powerful tool is the nanoparticle itself, materials like gold or silica, precisely engineered to carry therapeutic payloads. Their size and surface properties allow them to be directed to specific locations. Dendrimers, branched polymers, offer even greater control over drug release, allowing for a sustained and precisely timed delivery. But simply delivering a drug isn't enough. A major advance is the field of targeted therapies, aiming to make nanoparticles specifically recognize and bind to diseased tissues. Cancer cells, for example, often display unique proteins on their surfaces, proteins that can be targeted. Antibody-drug conjugates, ADCs, represent a brilliant example. Here, antibodies, which are designed to recognize specific cancer cell proteins, are linked to potent chemotherapy drugs. The antibody guides the drug directly to the cancer cell, minimizing damage to healthy tissue. Receptor-mediated targeting employs similar principles, utilizing nanoparticles coated with molecules that bind to receptors on infected cells or cancerous tissues. Beyond drug delivery, nanotechnology is also transforming medical imaging. Quantum dots, tiny semiconductor crystals, emit light of specific colors when excited, allowing doctors to see inside the body with exceptional clarity, far surpassing the resolution of traditional X-rays. They can be used to track drug delivery in real time, visualizing where the nanoparticles are going and how effectively they're working. Similarly, nanoparticles can be engineered to enhance MRI scans, providing clearer images of tumors or other abnormalities. Looking further ahead, scientists are exploring the possibility of nanobots, incredibly small robots capable of performing diagnostics and even targeted drug delivery within the body. While still largely theoretical, This vision holds enormous potential. Of course, with such powerful technology comes responsibility. Ensuring nanoparticle safety is paramount. Researchers are rigorously studying potential toxicity, examining how nanoparticles behave within the body and how they are eventually eliminated. Questions about long-term effects and potential accumulation remain active areas of investigation. Thorough testing and careful monitoring are essential to ensure that these microscopic marvels truly benefit patients and don't inadvertently cause harm. The future of medicine is undeniably intertwined with the advancements happening in the realm of nanotechnology. The relentless march of Moore's law, the observation that computing power doubles roughly every 2 years, has been a driving force in the electronics industry for decades. But as we've shrunk silicon transistors to their absolute limits, a new frontier has emerged: nanotechnology applied to electronics. The challenge now isn't just making smaller transistors, it's fundamentally rethinking how we build them and how we store and sense information. At the forefront of this revolution are carbon nanotube transistors, or CNTFETs. These transistors utilize individual carbon nanotubes, incredibly strong, hollow cylinders of pure carbon, as the conducting channel. What makes them so exciting? Electrons flow through carbon nanotubes with significantly higher mobility than silicon, meaning they move much faster. This translates to faster switching speeds and reduced energy consumption, a critical factor in modern devices. Furthermore, CNTFETs theoretically allow for thinner and more flexible electronics. However, creating CNTFETs isn't simple. The challenge lies in precisely controlling the electrical properties of each individual nanotube. Different nanotubes have different electrical characteristics depending on their structure, a property known as chirality, and achieving consistent performance across large arrays is a significant hurdle. Researchers are exploring methods to align and orient nanotubes precisely, and to create circuits where individual nanotubes can be selectively switched on and off. Beyond transistors, nanomaterials are transforming memory devices. Resistive RAM, RAM, for example, utilizes tiny nanowires, incredibly thin strands of material, often made from metal oxides, to store data. The resistance of these nanowires changes depending on the amount of current that flows through them, representing a 0 or a 1. This approach offers potential advantages over traditional flash memory, including faster speeds, lower power consumption, and improved density. And then there are sensors. The nanoscale offers unprecedented sensitivity to the environment. Nanosensors are being developed to detect incredibly small amounts of gases, chemicals, and even biological molecules, opening doors to a vast range of applications, from environmental monitoring to medical diagnostics. For instance, sensors incorporating quantum dots can detect specific chemicals by measuring changes in their fluorescence. Similarly, nanowire-based sensors are showing promise in detecting biomarkers for early disease detection. The pursuit of miniaturization isn't without its complexities. As devices shrink to the nanoscale, quantum effects, where the behavior of electrons is governed by probability rather than classical physics, become increasingly important. Heat dissipation is also a major concern. Smaller transistors generate more heat, which can significantly degrade their performance. To overcome these challenges, researchers are developing sophisticated nanofabrication techniques. Electron beam lithography, a process that uses a focused beam of electrons to precisely pattern materials at the nanoscale, is a cornerstone of this effort, allowing for the creation of incredibly intricate circuits and devices. Continued advancements in materials science and fabrication methods will undoubtedly shape the future of electronics, pushing the boundaries of what's possible at the atomic scale. Let's turn our attention now to a really exciting area of nanotechnology, how it's being used to clean up our planet. Scientists are harnessing the incredible properties of materials at the nanoscale to tackle some of the biggest environmental challenges we face. It's like having tiny, superpowered helpers working on a microscopic level. One of the most promising approaches involves nanoparticles. For example, iron nanoparticles are being developed to clean up contaminated water sources. These particles, when exposed to oxygen, create tiny bubbles that effectively strip away pollutants. Similarly, titanium dioxide nanoparticles, commonly found in paints, possess photocatalytic properties. When exposed to ultraviolet light, they break down organic pollutants like pesticides and dyes, converting them into harmless substances. The concept of nanofiltration is also gaining traction. Traditional filtration systems rely on pore sizes that are too large to effectively remove many contaminants. Nanofiltration, however, uses membranes with pores measured in nanometers, allowing them to capture far smaller particles, including heavy metals like lead and mercury, and even microscopic organic pollutants. This dramatically enhances the efficiency of water purification compared to conventional methods, allowing for cleaner drinking water and reduced industrial discharge. Beyond water, nanotechnology is offering solutions for air purification too. Researchers are exploring the use of nanostructured materials to capture and neutralize air pollutants. Photocatalytic nanoparticles, as mentioned, can be deployed in air purifiers, reacting with gases like nitrogen oxides and volatile organic compounds under sunlight. This is a particularly promising approach for reducing smog and improving air quality in urban areas. Another strategy involves using carbon nanotubes to filter out particulate matter, like soot and dust, from the air. However, it's crucial to acknowledge a significant concern: the potential environmental impact of nanoparticles themselves. While incredibly useful, the release of nanoparticles into the environment raises questions about their long-term effects. Some studies suggest that certain nanoparticles could accumulate in soil and water, potentially disrupting ecosystems. Careful research is ongoing to assess toxicity levels and understand how nanoparticles interact with living organisms. Therefore, responsible development and deployment are paramount. Scientists are focusing on creating biodegradable nanoparticles and developing robust methods for their safe disposal. This includes exploring techniques for capturing and removing nanoparticles from wastewater before they reach natural waterways. Furthermore, research is concentrating on understanding the mechanisms behind nanoparticle toxicity, allowing for the design of safer materials. Ultimately, the goal is to leverage nanotechnology's power to solve environmental problems while mitigating any potential risks. A delicate balance that requires ongoing innovation and a deep understanding of these tiny, powerful materials. Let's explore how we actually make these incredible nanoscale structures, how we build things smaller than a speck of dust, It's a surprisingly complex process, and there are really two main ways scientists and engineers approach it: top-down and bottom-up. Think of it like this. One approach starts with a big piece and carves away what isn't needed, while the other starts with tiny building blocks and carefully assembles them. The top-down method relies on precision removal. A common technique is electron beam lithography. We use a focused beam of electrons, much like a tiny, incredibly precise laser, to scan a pattern onto a material, usually a layer of polymer. The electron beam changes the polymer's chemical properties, making it either soluble or insoluble in a developing solution, depending on where the beam has been. This creates a mask-like pattern. Then we etch, remove the unprotected material using chemicals or plasma. Another powerful tool is focused ion beam milling, where a beam of ions, charged atoms, is used to selectively erode the material, again following a predefined pattern. Electron beam lithography and focused ion beam milling are excellent for creating very precise, intricate designs, but they can be slow and expensive, especially when scaling up to larger areas. They're fantastic for creating single-layer devices or small batches, but building larger structures this way becomes a significant challenge. The bottom-up approach takes a fundamentally different tack. Instead of carving away material, it builds structures atom by atom or molecule by molecule. Chemical vapor deposition, CVD, is a prime example. We introduce precursor gases containing the elements we want to form the nanoscale structure, for instance, carbon for nanotubes, into a heated chamber. The gases decompose, and the atoms deposit themselves onto a substrate, forming the desired material layer by layer. Self-assembly is another critical bottom-up method. Here, we design molecules with specific properties that cause them to spontaneously arrange themselves into ordered structures. Imagine tiny Lego bricks that automatically connect in a precise pattern. That's essentially what's happening at the nanoscale. Researchers are exploring diverse self-assembly strategies utilizing DNA, surfactants, and other molecules to build complex 3D structures. Each approach has its limitations. Top-down methods struggle with the inherent roughness at the nanoscale, which can introduce defects into the final product. Bottom-up techniques, while offering exquisite control, can be challenging to scale up. Ensuring consistent quality and yield across large areas is a constant hurdle. Currently, the cost of many nanofabrication techniques, particularly those using electron beams, is a significant barrier to widespread adoption. However, the future of nanofabrication is likely to be hybrid, combining the strengths of both top-down and bottom-up approaches. Researchers are experimenting with techniques like lift-and-grow, where a bottom-up structure is grown on a top-down patterned substrate, offering a route to creating complex, highly ordered nanoscale devices. Ultimately, achieving cost-effective and scalable nanofabrication will be key to unlocking the full potential of nanotechnology across a wide range of applications, from advanced electronics to revolutionary medical treatments. Let's shift our focus now to a fascinating area of nanotechnology: creating incredibly strong and efficient materials through composites. We've seen how tiny things can dramatically change electronics and even clean up pollution. But today we're exploring how nanoparticles are transforming the way we build everything from airplanes to buildings. The core idea is simple: add incredibly small reinforcements to existing materials, a process called nanocomposite formation, and you can dramatically enhance their performance. At the heart of this revolution are materials like carbon nanotubes and graphene. Carbon nanotubes are essentially rolled-up sheets of carbon atoms, incredibly strong and lightweight. Graphene, a single layer of these sheets, possesses similar exceptional properties. But simply adding these materials isn't enough. The key is how well they're dispersed and arranged within the surrounding material, often a polymer like epoxy or a metal alloy. Think of it like building a brick wall. If you just chuck bricks randomly at the wall, it won't be very strong. However, if you carefully arrange the bricks in a specific pattern, aligning them to share the load, the wall becomes incredibly robust. Similarly, nanoparticles in a composite can dramatically improve strength, stiffness, and even toughness, the ability to withstand impacts of the material. The alignment, in particular, is crucial. When carbon nanotubes or graphene sheets are aligned within the matrix, they can transfer stress more efficiently, preventing cracks from propagating. This technology isn't limited to just polymers and metals. Researchers are also exploring the use of nanoparticles in ceramics, increasing their strength and resistance to wear. For example, adding silicon dioxide nanoparticles to a ceramic matrix can create a composite that's far tougher than the ceramic alone. The impact of these nanocomposites is already being felt in several industries. In aerospace, lighter and stronger materials made with carbon nanotube-reinforced polymers are reducing aircraft weight and improving fuel efficiency. In the automotive industry, nanocomposites are being used to create stronger and lighter car bodies, contributing to better performance and safety. And in construction, we're seeing the incorporation of graphene-enhanced concrete, leading to structures that are more durable and resistant to weathering. Beyond carbon nanotubes and graphene, a range of other nanomaterials are finding their way into composite formulations. Metal oxides, like titanium dioxide, are used to enhance UV resistance and self-cleaning properties. Silver nanoparticles add antimicrobial characteristics. The possibilities are truly expanding as scientists continue to explore new combinations and techniques for incorporating these tiny reinforcements. It's a testament to how manipulating materials at the nanoscale can unlock extraordinary potential, shaping a future where materials are stronger, lighter, and more adaptable than ever before. The ongoing research also focuses heavily on optimizing the manufacturing processes to ensure consistent nanoparticle dispersion and alignment, a critical factor in achieving the maximum benefits of these advanced composites. The future of nanotechnology isn't about simply making things smaller. It's about fundamentally reshaping how we interact with matter and build technology. We're entering an era defined by incredible precision and the ability to design materials with properties never before seen. One particularly exciting area is DNA nanotechnology. Essentially, using the incredibly intricate and self-assembling properties of DNA to build nanoscale machines and structures. Scientists are designing tiny gears, switches, and even molecular robots, all crafted from strands of DNA, offering possibilities for targeted drug delivery and incredibly complex reaction systems. Beyond DNA, the concept of programmable matter is gaining serious traction. Imagine materials that can change their shape, stiffness, or even color on command, controlled by external stimuli like light or electricity. Researchers are developing materials composed of tiny, interconnected components that can rearrange themselves, potentially revolutionizing everything from adaptable clothing to self-healing structures. This moves beyond static nanomaterials to truly dynamic ones. The exploration of two-dimensional materials is also poised for explosive growth, with graphene's pioneering status now paving the way for a whole family of materials. While graphene's exceptional strength and conductivity are remarkable, scientists are actively investigating materials like hexagonal boron nitride (HBN), molybdenum disulfide (MoS2), and transition metal dichalcogenides (TMDs). Each possesses unique optical, electronic, and mechanical properties, offering specialized applications ranging from high-frequency transistors to advanced sensors. And what about computing? Nanoelectronics. Using nanoscale components to build transistors and circuits holds the potential to drastically increase processing speeds and reduce energy consumption. We're moving beyond silicon towards materials like carbon nanotubes and nanowires, which can conduct electricity with almost no resistance. This could lead to entirely new computing paradigms, moving away from the limitations of current chip designs and enabling quantum computing applications to become more accessible. The impact of nanotechnology isn't limited to traditional industries. We're seeing advancements in agriculture with nanoscale sensors monitoring soil conditions and delivering nutrients precisely where needed. In medicine, nanotechnology is driving personalized treatments and advanced diagnostics. Even the textile industry is being transformed with smart fabrics incorporating sensors and responsive materials. Crucially, artificial intelligence is accelerating the pace of nanomaterial discovery and design. Machine learning algorithms can sift through massive datasets of material properties, predicting the characteristics of new compounds and guiding experimental efforts, dramatically reducing the time and cost associated with finding novel nanomaterials. However, significant challenges remain. Scalability, producing nanomaterials in large quantities consistently and affordably, is a major hurdle. Reducing the cost of nanofabrication is another critical step. Furthermore, the regulatory landscape surrounding nanotechnology is still evolving, and ensuring safe handling and disposal of nanomaterials is paramount. Public perception also plays a vital role. Open communication and addressing concerns about potential risks are essential for fostering trust and acceptance. Despite these obstacles, the potential rewards of nanotechnology, a world of materials and technologies with unprecedented capabilities, are simply too significant to ignore. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. The world of nanotechnology, with its intricate building blocks, now gently fades from your awareness. Let your thoughts drift, calm and unhurried, like tiny particles themselves, until sleep finds you. Good night.